A numeric sequence is said to be statistically random when it contains no recognizable patterns or regularities. Sequences such as the results of an ideal dice roll, or the digits of pi exhibit statistical randomness. Statistical randomness does not necessarily imply true randomness, i.e., objective unpredictability. Pseudo-randomness is sufficient for many uses, such as statistics, hence the name statistical randomness. Global randomness and local randomness are different. Most philosophical conceptions of randomness are global, because they are based on the idea that, in the long run, a sequence looks truly random, even if certain subsequences would not look random. In a truly random sequence of numbers of sufficient length, for example, it is probable there would be long sequences of nothing but repeating numbers, though on the whole the sequence might be random. Local randomness refers to the idea that there can be minimum sequence lengths in which random distributions are approximated. Long stretches of the same numbers, even those generated by truly random processes, would diminish the local randomness of a sample. A sequence exhibiting a pattern is not thereby proved not statistically random. According to principles of Ramsey theory, sufficiently large objects must necessarily contain a given substructure. Chaos theorists disagree with Ramsey theory. Legislation concerning gambling imposes certain standards of statistical randomness to slot machines. Tests. The first tests for random numbers were published by M.G. Kendall and Bernard Babington Smith in the Journal of the Royal Statistical Society in 1938. They were built on statistical tools such as Pearson's chi-squared test that were developed to distinguish whether experimental phenomena matched their theoretical probabilities. Pearson developed his test originally by showing that a number of dice experiments by W.F.R. Weldon did not display random behavior. Kendall and Smith's original 4 tests were hypothesis tests, which took as their null hypothesis the idea that each number in a given random sequence had an equal chance of occurring, and that various other patterns in the data should be also distributed equiprobably. The frequency test was very basic, checking to make sure that there were roughly the same number of 0s, 1s, 2s, 3s, etc. The serial test did the same thing but for sequences of 2 digits at a time, comparing their observed frequencies with their hypothetical predictions were they equally distributed. The poker test tested for certain sequences of 5 numbers at a time based on hands in the game poker. The gap test looked at the distances between zeros. If a given sequence was able to pass all of these tests within a given degree of significance, then it was judged to be, in their words, locally random. Kendall and Smith differentiated local randomness from true randomness, in that many sequences generated with truly random methods might not display local randomness to a given degree. Very large sequences might contain many rows of a single digit. This might be random on the scale of the entire sequence, but in a smaller block it would not be random, and would be useless for a number of statistical applications. As random number sets became more and more common, more tests of increasing sophistication were used. Some modern tests plot random digits as points on a 3-dimensional plane, which can then be rotated to look for hidden patterns. In 1995, the statistician George Marsaglia created a set of tests known as the die-hard tests, which he distributes with a CD-ROM of 5 billion pseudorandom numbers. In 2015, Yuanga Wang distributed a Java software package for statistically distance-based randomness testing. Pseudorandom number generators require testers exclusive verifications for their randomness, as they are decidedly not produced by truly random processes, but rather by deterministic algorithms. Over the history of random number generation, many sources of numbers thought to appear random under testing have later been discovered to be very non-random when subjected to certain types of tests. The notion of quasi-random numbers was developed to circumvent some of these problems. Though pseudo-random number generators are still extensively used in many applications, as they are good enough for most applications. Other tests. The monobit test treats each output bit of the random number generator as a coin flip test, and determine if the observed number of heads and tails are close to the expected 50% frequency. The number of heads in a coin flip trail forms a binomial distribution. The Wald-Wolfowitz-Runz test tests for the number of bit transitions between 0 bits and 1 bits, comparing the observed frequencies with expected frequency of a random bit sequence. Information entropy. Autocorrelation test. Kolmogorov-Smirnov test. Statistically distance-based randomness test. Younger-Wang showed that NIST SP 800-22 testing standards are not sufficient to detect some weakness in randomness generators and proposed statistically distance-based randomness test. The spectral test. Maurer's universal statistical test.